Tyler here at USC. I will be going through some physics concepts and examples with you this semester. And remember, just like on the ice, there's no such thing as luck in physics. Just keep your head up and work hard.
Let's look at the following example to see why are we interested in dot product in the first place. So what we have here is the classic problem of pulling a box on the floor. So we neglect friction, so pretty much only the two forces that are acting here is the gravity that is keeping it on the floor, and then we have this force F that we are pulling the box with, and it's inclined by 45 degrees. And we pull this box until, or we pull it some distance, and let's call the displacement vector S. So we pull it for, let's say, 2 meters along the floor. Now the question is, how much mechanical work is being done on the box? The definition of mechanical work, or one of them, is in fact Fs, as you might have seen, but this is a simplification. The actual form of the mechanical work is F dot S. So the dot product of the force that is acting on the box with the displacement vector. So as we saw from the previous page, or the previous slide, this is same as F times S times the angle between the two. Let's say F is the magnitude of S, F is 100 newtons. So we get 100 newtons times S, which is 2.0 meters, times the angle between the two, cosine 45. And this is about 141.4 Newton meters. We have let's see, we have one. Okay, let's put it 2 significant digits. So 140. And what is Newton meter? That is a joule. So we do a work of 140 joules. Well, let's calculate the dot product in the other way we learned. So first of all, we have our vector F and S intercomponents. So this is Fx times I. So here we have x-axis and y-axis, and then also the y component like this. And what is Fx? So well, that's F times the component in the x direction, or times the angle between the x direction and the vector itself. So that's going to be cosine 45 I plus Fy, same thing, F times the sine of this angle in the j direction. And then S, it has in fact only the x component in the I direction, so the x component itself is 2 meters. Like this. And now the other definition of the dot product, of course we're interested in the work, so vector F dot S vector, as we learned, it's just a multiplication of the respective vectors. So here we have Fx times Sx plus Fy times Sy. And what is Fx? So that's F times cosine 45 degrees times Sx. And here we would have Fy times Sy, but as we know, there's no displacement in the y direction, so that is 0. So again, 100 newtons times cosine 45 degrees times Sx, just the 2 meters. Like here, we get about 140 joules. More interesting than the fact that we got the same result is this here. So pretty much what this is saying is that the work done in the y direction is 0. And that is because the displacement has no component in that direction. So using the dot product, we are only picking up the component of force F in the direction of the S, and that is all that matters. So the dot product nicely takes into account that the F is not aligned with S, like we have usually calculated in high school physics, but there's an angle, and that is embedded into the definition of the dot product, that the angle can be there, and in that case it only takes into account the component in the direction of the displacement.